Okay, here we are, assignment 9. First section of the 10 different sets of mops you have to do. Here are 2 questions. Why don't you answer them and then we can go over them. So P, momentum is a vector, velocity is a vector, it has a direction. It's simply the mass and the velocity that determines the momentum. Force has to do with impulse, we'll talk about that. Resistance to a state of motion, do you recognize that? That's mass, inertia. Moving fast, that's velocity, but you have to have mass. Changing velocity, that's changing momentum or impulse, and we'll talk about that. So this is the answer. And same thing down here. Encountering a force changes the momentum. Slowing down means the momentum is changing. Speeding up means the momentum is changing. An object has to be moving. It doesn't have to be changing. It doesn't have to be moving fast. So mass and motion. How about units? Units are important conceptually and mathematically. So MV, kilogram, meters per second. There's no shorthand. And we'll see later that a Newton second is the same units, but that's used for impulse, which is force times time. So they have the same units, but the impulse, although it has the same units, is in fact a different quantity than momentum, which has these units. So where is it? Kilogram times meters per second. So answer questions 16 and 20 and then see what I say. So a rightward moving object has a rightward momentum because momentum is mass times velocity. So the direction of the velocity is the direction of momentum. A rightward moving object that's slowing down has a velocity which is rightward, an acceleration which is leftward, and a force which is leftward, and a momentum which is decreasing. But the question is the direction of the momentum, and that's always in the direction of the velocity. In order to have a lot of momentum, a lot of mass, if you have a lot of mass but you're at rest, that's no momentum. Moving fast, if you're an electron moving fast, that's very little momentum. Changing very rapidly, that's a rapidly changing momentum. Tells you nothing about the momentum. Encountering a large force means the momentum's changing, but doesn't tell you anything about the momentum. And exceeding the speed limit, well, that's a joke. So the answer, surprisingly, is nonsense. We can't really be sure from any of these that an object has a lot of momentum. It would have to have substantial mass and substantial velocity both. Or if a small velocity, a very, very large. If a small velocity, a very large mass, or vice versa. So you do need more information. This one's fairly easy. See what you get. You got 2 times 2 is 4 kilogram meters per second and 16 kilogram meters per second. So object compared to object B, object A is 4 times 1/4. Object A is 1/4 the momentum of object B. At any given instant of time, the momentum of an object depends on, list all that apply in alphabetical order. How fast? Does depend on how fast, yes. How rapidly accelerating? No. If the velocity is low, the velocity can be low, but it can have a high acceleration. How much mass it has? Yes. The force is experiencing? No. That has to do with the impulse and the changing momentum. Right? And the rate at which an object is changing its velocity? No, remember, we're going to see this soon. Impulse is the net force times the time, and that is equal to the change in momentum. But not the momentum. The momentum can be changing, but doesn't tell you how much momentum there is. And the time is also related to the impulse. So these are related to impulse, which is the next section. So here's a couple questions on impulse that you can answer. Okay, so here we are in the second set of exercises, which has to do with impulse and momentum change. We talked a little bit about that. Let's just review all this. So the definition of momentum is simple. Just remember that it's a vector. Remember what the units are, kilogram meters per second. And then if we look at Newton's second law, we say the sum of the forces, or the net force acting on an object, is the mass times its acceleration. Notice the mass times the change in velocity over the change in time. That's the acceleration. And if we rearrange this equation, we get that the force acting times the time interval over which it acts is equal to the mass times the change in velocity. And so that quantity, mass times change in velocity, is the change in momentum. And by this law, it happens to be equal to this product of force and time, which we call, sometimes we use the symbol J, it is a vector, or I'll call it impulse or IMP. So this is our definition of impulse. What determines the impulse is the force acting and the time over which it acts. This would be our definition of momentum and change in momentum, and they are always equal. And a further extension that we'll see a little bit later is that if the force acting on an object is zero, there'll be no change in momentum. But in collisions between two objects that are isolated from the surrounding environments because they're frictionless or something like that, the two objects will change momentum, but the system of objects will have its momentum conserved. Because if no outside force acts on an isolated system, then there's no change in momentum. So when the two balls collide, the momentum of each ball will change, but the loss of momentum of ball 1 will be equal to the gain of momentum of ball 2. We'll see this later, and that means that delta P equals 0, or P initial equals P final. And so remember, the momentum of each object can change, but whatever the loss of momentum of 1 is, that will be the gain of momentum of 2, and we will have this condition that momentum is conserved, and we call that the law of conservation of momentum. Okay, so that's what we're going to be using throughout all these exercises. This particular one on impulse and momentum changes involves the definition of impulse, the definition of changing momentum, and the fact that they are equal to each other. That's called the impulse-momentum theorem. Okay, with that in mind, answer the first two questions here. So based on what we just said, impulse is the force acting over the time interval that acts, occurs when a force is acting upon an object for a given amount of time in order to cause, what does that result in? A change in momentum. And the units of impulse are Newton seconds, force times time. Now notice a Newton is a kilogram meter per second squared, and if you multiply that by a second, you get kilogram meters per per second, which are the units. So they are equivalent. So momentum, change in momentum, and impulse do in fact have the same units. And newtons times seconds are equal to kilogram meters per second. But generally we prefer to write it this way when talking about impulse, and this way when we're talking about momentum. So following what we just said, in a collision an object experiences an impulse. The impulse causes and is equal to the momentum change of the object. So pause the video and answer this one and see if you can get it right. Okay, let's see. Multiplying force by time. Yep, that's impulse. Multiplying the force times the mass. No, that's nothing. Multiplying the mass times the acceleration. That's force, not impulse. Multiplying the mass of an object by the velocity change. That's change in momentum. Oh, yes. Change in momentum is equal to the impulse. Dividing the force by the time? No. Dividing the force by the mass? No, that's acceleration. Dividing the force by the acceleration? No, that's mass. Dividing the momentum time by the change, that would be force. So there are your two answers. Okay, here are 3 questions. Pause the video and answer them. In a collision, an impulse in an object is equal to its momentum change. It's not equal to its momentum. In a collision, an impulse encountered by an object is equal to its momentum change. Yes. 2 kilogram, 5 meters per second. That's 10 kilogram meters per second of momentum. A 30 Newton resistive force for 1/10 of a second, so the force is 30 newtons. The time is 1/10 of a second. So what do we get? We get 3 Newton seconds. That's the impulse. So the impulse is 3. What's the momentum? 10. What's the change in momentum? Resistive force. So it's going to be -3. Actually, the impulse should be -2. And so the change in momentum, there's a loss of momentum. And so the P final would be 7 kilogram meters per second, because the impulse is equal to the change in momentum. Okay, 2 more for practice. Read and answer. So the first one, I did it out. 3 momentum mass times velocity, 18 kilogram meters per second. The impulse, however, is the force times the time, so 20 times 1/10 is -2 kilogram meters per second, or 2 Newton seconds, same thing. Delta P is equal to the impulse, so that's a -2 kilogram meters per second, which is equal to P final minus P initial. So if we add P initial to both sides, we get that P final equals P initial, 18, plus delta P, -2, so 16, right? You're going to be a little careful with the minus sign. It did decrease. And if we go down to the next one, we have a 4 kilogram object. So this one is 24 kilogram meters per second, right? And 2 newtons for 2/10 of a second, so that's -4 resistive force, -4 Newton seconds or kilogram meters per second. So the final momentum is going to be the initial minus, or the added, with the change added, but the change is negative. So we would end up with a final momentum of 20. Let's see if it's there. per second. Okay, now we're down to section 3. Okay, section 3, more on impulse and momentum change. Impulse, force times time, momentum change, impulse momentum theorem. Take a look at these two questions and see what your answers are. First question, more time, more momentum change. So if the contact time were increased by a factor of 2, then the impulse would double, f dot dt, and the resulting momentum change would also double because the change by the impulse momentum theorem, what we saw earlier, the change in momentum is equal to the impulse. That's why when you throw a baseball, you want to follow through. The longer the ball is in your arm, the more time you exert a force on it, the more momentum and velocity it gets. Crumple zones, airbags, sand-filled plastic barriers all do one thing. They extend the time of stopping. They extend when you go from an initial momentum to 0 momentum. That's a change in momentum, and that requires a force and a time. And the change in momentum is whatever your momentum was to 0. That doesn't change, but if the time is short, the force will have to be big. Supposing the momentum change were 10 units, if the time is 1, the force has to be 10. If the time is 1/10, the force has to be 100. So the longer the time, the less the force. So the force it takes to stop when you stop your car slowly is little. If your car stops abruptly in a short period of time, like hitting a concrete wall, then the force on the car and on you is going to be very, very high. Okay, anyway, let's answer the question. All right, I just noticed there were more choices. So the crumple zone, the safety feature does what? It protects the passenger by increasing, first blank, the time over which the collision occurs, and so that's A, and decreasing, second blank, the force acting on the passenger. So I. Now notice, you may be tricked. You can't change the velocity. So remember, you're moving along at a certain velocity, and then you stop. So the change in velocity is fixed. You go from whatever velocity you are to the end. And since the change in velocity is determined by the situation, you can't control that. It means that the impulse, the change in velocity, and thus the change in momentum are all fixed. You can't lower or increase or decrease those. But that impulse and change in momentum is equal to the product of force and time, and those are the two things that can be changed. So by using the crumple zone or the airbag, you lengthen the time and you decrease the force, because the product has to be equal to something that is a constant that you can't control. So same thing on question 9. You increase the time over which the collision occurs, and since the product, the impulse, is constant, that will decrease the force acting on the passenger in the car. Actually, putting some numbers in might help the situation. So 60 kilogram object is moving at 20 meters per second. So that's 60 times 20. That's 1,200 units of momentum. And when it's brought to rest, that goes to 0. So the final is 0, the initial, so that's a change in momentum of a negative 1,200 newtons. And so that amount of change in momentum has to come from a force and a time. And so if the time were a half a second, then that means the force would be 2,400 newtons. But if the time were only a 20th of a second, if it were 10 times shorter, the force in that case would have to be 10 times bigger. It'd have to be 24,000 newtons. And so if the object initial speed were brought to rest in that amount of time, the required force would be 10 times the original value. No, 1/10, because they're giving us the longer time, second. So if we're brought to rest in a longer period, a half a second isn't, but if you hit a concrete wall, you might stop in 1/20th of a second, whereas if you hit something with the crumple zone, it may lengthen the time a half a second. And in that case, the force acting on the car and the passenger would be 1/10 the value. The resulting impulse would be the same. That's what, can't change that. The impulse is negative 1,200. The change in momentum is negative 1,200. That's the whole idea, is you have no control over that and the resulting momentum change. Okay. So these last two questions from section 3, before we move on to section 4, read through them. They're very similar, and so they're going to answer the same way. So read through them and see what your answer is and think about your reasoning. Okay, so these are very similar. One ball drops and hits the ground and stops, and the other ball hits the ground and bounces back. So it's easy to understand if we give this number. Suppose the ball is 1 kilogram, and suppose it hits the ground at 10 meters per second. Then just before it touches the ground, it's going 10 meters per second times 1 kilogram, so that's 10 units of momentum, which goes to 0. The ball that bounces back hits the ground with 10 units of momentum, but then it bounces back with a velocity, say, of 8, because it goes to 80.8 meters. And so the change in momentum of the second ball is P final, so it's going backwards, so that's negative 8 units of momentum, and you subtract the original 10, that's a change of 18. So the ball that bounces undergoes a bigger change in momentum. If it bounced back all the way, it would be double the change in momentum of the ball that just hits. And so it's the same thing if you throw a ball against a wall and it just stops. That change in momentum is less than if you throw the ball against the wall and it bounces back. And you can see that if a ball goes into the wall at 5 meters per second and comes back at 4, the change in velocity is the final 4 minus the initial. This is, well, let's say this is positive, then it comes back negative, minus the initial. That's a change of negative 9, whereas the ball that hits the wall and stops has a final of 0, and you subtract 5, and it's a change of negative 5. So the change in velocity and the change in momentum of the ball that stops is going to be less than the ball that bounces back. So answering the question, if we compared to the sad ball, the ball that doesn't bounce, the happy ball has a greater velocity change, therefore, same mass, a greater momentum change, and therefore a greater impact force, assuming that the collision times are the same. And similarly here, if we compare ball A, would hitch the wall and rebound, ball B, which hits the wall and stops, ball B has a smaller velocity change, it didn't bounce back, a smaller momentum change, and a smaller impact force. Okay, here we are in number 4, but I've run out of time and I want to get this posted, so even though we've only done 3 out of 10, I'm going to post this and then I'll update it tomorrow when I'm able to finish more of these.